Okay, so what we want to show in this video is the relationship that is displayed between the beta and the gamma function. So I have listed both functions in their integral forms, and since we're trying to somehow get from gamma to beta function, what I'm going to do is actually I'm going to start with gamma of alpha multiplied by gamma of beta. Let's see where this is going to take us. Now gamma of alpha is by definition the integral from 0 to infinity of x to the alpha minus 1 e to negative x dx. And we're going to times it by gamma of beta, which is similarly written as integral from 0 to infinity of y. We got to choose a different variable for the gamma of beta because they could possibly be different, alpha and beta. And this is going to be y to the beta minus 1 times e to negative y dy. And for both of these, x and y, the domain is all positive values. Okay, so what is next? Next, we're going to join these two integrals together as one. So when we join them, we're going to get the double integral from 0 to infinity of x to the alpha minus 1 times y to the beta minus 1. And then the exponents, e to negative x, e to negative y, we can combine them using the multiplication rule of exponents as e to negative x plus y, and then it'll be dy dx. Okay, now at this point we're going to make a transformation, okay, to be able to work this double integral. And here we're trying to find something that relates the exponent x plus y in e to the negative x plus y. So my proposed transformation is going to transform x from a region in the xy plane to a region in uv plane. So capital T here represents a transportation of a point, a mapping from xy region to a uv region. And for our transformation, we're going to let x be uv. So I have a function of u and v. And we're going to let y, this is the most common transformation, u minus uv, which also can be written as u times 1 minus v. So this is a different function of uv. So you can see again under this transformation, x and y, each of them are transformed into a region, a different region. So next step, we're just going to add these two equations. Okay, so let's say we want to add them. On the left, we get x plus y, which is the exponent on e that we were seeking. When you add this, the right side, uv, negative uv, those are opposites, they add to 0. So we actually have found u in terms of x and y. And from this, since x is uv, we can replace u with x plus y that we just found times v and divide both sides by x plus y, and we actually have now v as a function of x and y. The reason we need to do this is because we need to, under this new transformation, we need to be able to find the limits of integration. The limits of integration under the transformation is going to be the domain of u and v. So our next natural question is, what is the domain of u and v? Okay, so this one is a bit tricky, but we can handle it. Now looking at these expressions for u and v, well, u is pretty easy, straightforward. Let's do that one. Because u is the sum of xy, and x and y each were between 0 and infinity, right? So it makes sense that u, that would be the domain of u. U lies between 0 and infinity. So that takes care of u. Now v is done differently. Okay, to determine the domain of v, we write v here again, which is x over x plus y. So here's how I went about it. I'm going to keep x fixed for a fixed x. We're going to let y approach infinity. Okay, remember each x and y lie between 0 and infinity, so that's what I'm trying out. what if x is fixed and we let y go to infinity, where clearly we have a constant if x is fixed, constant in the numerator, y goes to infinity, therefore clearly the ratio approaches 0. It's going to be a constant over something very large. So v approaches 0. And then next I'm going to say, well, what if we fix y and we let x run to infinity, gets very large? Well, for a fixed y, the ratio is going to be like x to x plus a constant, let's say, and that ratio is 1. So v approaches 1. Okay, well that's good. V approaches 0, v approaches 1. That's not enough yet to establish the domain of v. Now the question that will seal this for us is, well, will v approach 1 from the right or from the left? Okay, so let's see how that's going to work out. To address that question, I'm going to let x approach infinity and y approach infinity, both of those. Now, as x and y approach infinity in here, clearly the denominator is bigger than the numerator, right? We can see that. A larger denominator and a smaller numerator. But that ratio, because the denominator is bigger than the numerator, the ratio is going to be less than 1, true? So v is going to be less than 1. And the fact that it's less than 1 tells me that v is approaching 1 from the left. Now, putting this information, all of this together, we can establish the following relationship, that v lies between 0 and 1. And that's the key relationship we wanted to determine the domain of v. Okay, so what is going on geometrically with this transformation? It'll be interesting to kind of see what's going on. So what we have done in effect is this. Suppose x and y, remember they were both positive. So we have a region in Q1 in the first quadrant. And this is a point, called it x, y, in the first quadrant. Okay, so what happens, and the shaded region is an RXY, right? The region in XY. Now, we're going to make a transformation that we just made, and that transformation is going to take that typical value of XY, that ordered pair. We're going to U and V. So under R, U, V, the region in U and V, well, V runs between 0 and 1. There you go. And U is between 0 and infinity, right? So that's going to give us such a region. And that XY now corresponds to a point in UV. Okay, so that's what this transformation has done for us. So it's good to see the geometry of what just happened. And it is a one-to-one transformation, so we are allowed to move to the next step. Okay, having done that, next I'm going to recall the relationship between the integral in the region xy given by a joint function f of xy dy dx. That integral is going to be equal to the double integral in region RUV under the transformation. And now we're going to have a function of UV, and then of course the absolute value of J du dv, where J here is, if you remember, J is known as the Jacobian of this transformation. Okay, so we are making a, again, mathematical transformation. So what we need to do next, because we pretty much have established the limits of integration for the new transformation, what we need is to measure the Jacobian, right? Find out what the Jacobian is, and let me just go ahead and rewrite what x and y were under this transformation. So how do we find the Jacobian? Well, the Jacobian of the transformation, if you recall, is given by dxy over duv. Okay, and specific of this is going to be the determinant, this is not absolute value symbol. This is the determinant notation. It's going to be the determinant of dx du, and then we have dx dv over dy du and dy dv. So that is what the Jacobian is. So that means we need to take the partial derivative of x with respect to u. So if you look at this right here, when you take the derivative of x with respect to u, we're going to have v. And if you take the derivative of x with respect to v now in the same, we're just going to simply get u. All right. And then once we're done with that, we're going to do the same thing with y. Take the partial of y with respect to u, we're just going to have 1 minus v, and take the partial of y with respect to v, we're just going to get negative of u. Okay, and the reason again here, if you distribute, that will help you see it a little easier. So the partial with respect to v is just going to be negative u here. Okay, and the determinant, if you recall the 2 by 2 determinant, you multiply the diagonal elements minus the product of the off diagonal. And to carry this a bit further, we're going to get this relationship. UVs become opposite, so the Jacobian of our transformation is simply negative u. Okay, now we're going to carry all of this to our double integral now. Therefore, gamma of alpha and gamma of beta, that's going to give us the double integral. And I'm going to go with u first, v second. So it's going to be the integral from 0 to 1. That's for u. The limits of integration on v, and then we have 0 to 1 was the limit of integration for v actually, and the limits of integration on u were 0 to infinity. Replacing x with our transformed variable uv to the alpha minus 1, right? And then times we had v to we had y to beta minus 1, but then y is going to be u times 1 minus v to beta minus 1, okay, times e to, remember the exponent on e was x plus y, right? Negative x plus y, so here's negative x, and then I'm going to add y to it, which is u minus uv. And then times the Jacobian. The Jacobian was absolute value of Jacobian, negative u here. And then, of course, sorry, I'm running out of space here. Let me shrink this a bit. There you go. Times, and we're going to write du dv. And there we have it. Now, some things get simplified here, of course, in the exponent. We're just going to have e to negative u. Therefore, the double integral becomes 0 to 1 and 0 to infinity of u to the alpha minus 1 plus beta minus 1. So I'm doing the u here and the u here. Using multiplication rule of exponents, that's what I get. All right. And then we come to v times v to alpha minus 1 times 1 minus v to beta minus 1, and this is just e to negative u. True. Absolute value of negative u is going to be u, and then du dv. Okay, so what is the next step? The next step, we can actually combine this. We have a u here and we have this u here. True. So we can combine those. And let's see what we're going to get here. So this is going to become the double integral from 0 to 1. And I'm going to go ahead and separate. I'm going to put the variable v under v to alpha minus 1, 1 minus v to beta minus 1. So I'm going to write the joint integral as product of two individual integrals. dv, and then we're going to multiply this by the integral from 0 to infinity of u2 alpha plus beta minus 1. Remember, the u here and one of the u's here combine, and that's how we only have -1 now in the exponent. Okay, and then of course we have times e to negative u, and this is going to be du. Good, so it's looking good actually this so far. Now we can recognize this as a beta, right? That integral is simply beta of alpha beta, and this integral is our gamma function, gamma of alpha plus beta, because the exponent on u is alpha plus beta minus 1. Thus we can write the following relationship. We can say that gamma alpha times gamma of beta is equal to the beta function times the gamma of alpha plus beta, and you kind of see where that's going. Therefore, beta of alpha beta, divide both sides by gamma of alpha plus gamma beta. That's going to give us the desired relationship that we were looking for, and this is what we want. Okay, now so that was the purpose of this video. So I'm going to give you a couple of examples here to see the utility of this. But one thing I want to note is that, let me just put a note here. Note, if alpha and beta are positive integers, so let's call these positive integers, alpha, beta, then gamma of alpha is going to be alpha minus 1 factorial, and gamma of beta would be beta minus 1 factorial. In general, gamma of anything positive integer is going to be the positive integer minus 1 factorial. And thus in the denominator I can write gamma alpha plus beta as alpha plus beta minus 1 factorial. So you may see this relationship in terms of factorials also. So let's take a look at an example and see how we can actually take advantage of this to evaluate some integrals. First, I'm going to just try this relationship. I want to find beta of 5, 7. Now beta 5, 7, that means gamma 5 times gamma of 7, and then in the denominator you combine 5 and 7, we get 12. Because both 5 and 7 are positive integer, then we can go gamma of 5 is 4 factorial divided by, or times 6 factorial divided by 11 factorial. Subtract 1 from each of those and factorial them. And then when you do this factorial, you can work it on your calculator or by hand. It's not difficult even by hand. You get 1 over 2,310. Okay, that's what that is. So now let's relate this to an integral. So suppose we have beta 5, 7, and according to the definition of beta function, that's the integral from 0 to 1 of x2. Remember, the exponent is alpha minus 1. Here alpha is 5, beta is 7. So alpha minus 1 is 4, and 1 minus x2, beta minus 1, 7 minus 1 would be 6 dx. So if I want to evaluate this integral, rather than expanding the binomial to the 6th power, distribute x to the 4th times it, combine like terms, and proceed with integration, we can just call this as 4 factorial, 6 factorial, 11 factorial. Again, this works with a very limited number of integrals, but it's interesting that we can actually do that rather quickly if you can recall this relationship. But it's important, the limits of integration also, they have to cooperate. It's got to be between 0 and 1 for this to work. For another limits of integration, this is not going to work. And there you have it. So we did what we wanted to do, and that we wanted to establish the relationship between the beta function and the gamma function. Thank you for watching, and that will conclude this video.